Today we're going to be talking about section 7.4, singular value decomposition. So in our previous video for sections 5.3, we talked about how to diagonalize a matrix. So the idea here is that if you have a square matrix and you can factor it into a product that includes a diagonal matrix, then you can analyze your matrix A by using that much simpler diagonal matrix. Unfortunately, as we saw in section 5.3, even if you have a square matrix, it's not guaranteed that you'll be able to diagonalize it. And if you have a non-square matrix, then our process didn't work at all. So our goal for today is to come up with some way to quote-unquote diagonalize these matrices that are either non-diagonal or even non-square. So we want to take any matrix that you might hand us and be able to diagonalize that matrix in some sense of the word diagonalization. So factor it into something where you have a simpler matrix that is easier to analyze. And this is what singular value decomposition is, and it is probably the most important and useful factorization style of matrices that exists in linear algebra. So to get there, we're going to need a bunch of things that we skipped. So we're going to spend the first roughly half of the video talking about these background things. So when I say we're talking about section 7.4, I mean sort of nominally. So we're going to be touching on a couple of things from section 6.1, 6.2, and 7.1. So that being said, we're not going to go into a huge amount of depth in any of this. So you are going to be responsible for what is in this video and not the extra things in the textbook that we don't cover. All right, so let's get started. So we're going to start off with the definition from 6.1, which is the inner product or the dot product. And we've seen this before. The inner product is just doing a matrix multiplication where we take U transpose times V between two vectors. That's a fancy way of just saying you take the first component of each vector and multiply it, and then add to that the product of the second component, and add to that the product of the third component, and so on. And this is a scalar. Two vectors, U and V, are said to be orthogonal if their dot product is 0. So let's take a look at an example where we see what a dot product is and then see how to measure if something is orthogonal. Incidentally, if you're thinking of this geometrically, orthogonal just means these two vectors are, in a sense, perpendicular to each other. So they have a 90-degree angle in between them. All right, so we're looking at problem 16 from section 6.1. And our question is, are these two vectors orthogonal? So what we're going to do is just take the dot product of them and see if it's 0. If it is, they're orthogonal. If not, they're not. So to take the dot product, we look at U transpose times V, which in this case, U transpose will give us a row vector, 12, 3, minus 5 times V, which is 2, minus 3, 3. And this will give us a 1-by-1 matrix or a scalar. That gives us 12 times 2 is 24, minus 9, minus 15, which does indeed give us 0. So the answer to this is yes, they are orthogonal to each other. So as you see, a dot product is just what we've been doing all along. It's a simpler version, if you will, of matrix multiplication. Okay, so we know how to take the dot product of two vectors, and now we know what they mean to be orthogonal. That means the two vectors are perpendicular, their dot product is 0. Another thing we can ask is, how long is a vector? What is its magnitude? Remember, a vector is a combination of direction and magnitude, so our question is, what is its magnitude? The length of a vector is the square root of its dot product with itself. So if you think of taking the dot product of a vector with itself, then you're just squaring each of those components and adding them up. That's what the second piece is. And we call something a unit vector if it has length 1. So something we might want to do is we might want to normalize a vector. So we might want to say, I like the direction that this vector is pointing, but I'd like it to have a magnitude of 1 instead of whatever magnitude it has. And we can normalize a vector, that is, turn it into a unit vector by dividing it by its own length. So we can get a unit vector pointing in the same direction if we take that vector and divide it by its length. So let's try this out. This is problem 10 from section 6.1, and it wants you to find a unit vector in the direction of this vector -6, 4, -3. So in order to do that, we first want to find the magnitude of this vector v. So the magnitude is going to give us the square root of each of those components squared. So -6 squared is 36, plus 4, 36, not 36 squared. -6 squared is 36, plus 4 squared is 16, plus -3 squared is 9. So if you add all of those up, you should get 61. So the magnitude here of this vector is square root of 61. So if we want to find the unit vector, then all we do is we divide our vector v by the square root of 61. So we take every component in the vector v and divide it by square root of 61. So our new vector is -6 divided by the square root of 61, 4 divided by the square root of 61, and -3 divided by the square root of 61. So this still points in the same direction, but now it has length 1. Okay, so we've talked about what it means for a vector to be orthogonal, and we've talked about what it means for a vector to have unit length, and we can combine both of these things into something called orthonormal. So let's start off. If we have a set of vectors in Rn, we've now moved on to section 6.2. If you have a set of vectors in Rn, this is an orthogonal set if every pair of vectors is orthogonal. So everything is perpendicular to each other. So if you take any pair of vectors and you take their dot product, that'll equal 0. And it's orthonormal if it's both orthogonal and every single vector is a unit vector. So let's say we have a set of 3 vectors, and let's suppose this set is orthonormal. Well, we have a bunch of, I've already written out what all of the pairs could be, and we're going to think about what should their dot product be. Well, if I have u1 dotted with u2, then those should be perpendicular to each other, so that should be 0. That's because we want this set to be orthogonal. u1 could also be dotted with u3, that should also be 0, and u2 could be dotted with u3, that's also 0. So that's all of the pairs of vectors in here. We could also dot these with themselves. So u1 dotted with u1, what should that be? Well, we want this to be orthonormal, so we want its length to be 1. So each of these vectors should be a unit vector, and if you look at the length equaling 1, that would be the square root of the dot product with itself, but the square root of, if we square that, we would just still get 1. So u1 dotted with u1 should still be 1. u2 dotted with u2 should be 1. u3 dotted with u3 should be 1. So all of the 1s tell us that this is a normal set, and all of the 0s tell us it's orthogonal. So together that's an orthonormal set. Okay, so we're now in section 7.1, and section 7.1 talks about symmetric matrices. So a matrix is symmetric if it equals its own transpose. And this sounds confusing, but it's actually a pretty intuitive definition. So let's say we want to build a symmetric matrix. So let's say our first row of our matrix is 1, 2, 3. If this matrix is going to equal its transpose, that first column should be the same thing as its first row. So our first column should also be 1, 2, 3. And if we look at that, there is a symmetry there. That's why we call this symmetric. So now let's say the second row, we already know the first entry needs to be a 2, but let's say we have it 2, 4, 5. Then the second column should be the same as the second row. So the second column should also be 2, 4, 5. We can finish it up here. So this is a symmetric matrix. This is symmetric because if you took the transpose of this, it would equal itself. And you can visually look at things and tell they're symmetric because the off-diagonal entries all come in pairs. Now, if we have a matrix that's symmetric, then eigenvectors that come from different eigenspaces are automatically orthogonal. So if you take eigenvectors from 2 different eigenspaces, this was what we were doing in the last video, we automatically know that if we dot them together, we'll get 0. Those are perpendicular vectors. Another fact is that every n by n symmetric matrix is diagonalizable. So we saw in section 5.3 that we can have square matrices that aren't diagonalizable. But if your square matrix is symmetric, you're automatically diagonalizable. So you automatically can be factored into that P, D, P inverse, where D is diagonal. In fact, because our eigenvectors are what makes up P, and we just saw that if your symmetric eigenvectors from different eigenspaces are orthogonal, it's possible to have your P be entirely made up of orthogonal columns. And if you take the unit vectors of those, if you normalize all of those vectors, you can have P be an orthonormal set. So not only is that symmetric matrix diagonalizable, it's in fact sort of a super fancy special diagonalizable called orthogonally diagonalizable. Okay, so to recap, here was our background that we were building up. We talked about vectors being orthogonal, so that means they're perpendicular, their dot product is 0. We talked about vectors having unit length, and if you had a set of vectors that was both orthogonal with unit length, those were orthonormal. And we also talked about what it means for a matrix to be symmetric. So we're going to pull all those pieces together and use those to talk about how do we, quote unquote, diagonalize any arbitrary matrix. So we're now starting with 7.4. So we're going to let A be an m by n matrix, so any random matrix we want. And we want to diagonalize it in some sense. So something to note is that A transpose, since A was an m by n, A transpose should be an n by m. And if we multiply A transpose times A, then we should get a square n by n matrix. And in fact, if we take a look at the transpose of that product, so A transpose A transpose, then we can recall from our properties of transposes that the transpose, when you take the transpose of a product, you apply that transpose backwards in a sense. So we'll apply the transpose to A and then apply the transpose to A transpose. And A transpose transpose is just A. So what does this mean? The transpose of that product is itself. So A transpose A is a symmetric matrix. So that means that even though A was arbitrary, we started off with a completely random A. If we take a product with its transpose, then that's symmetric. And every symmetric matrix is diagonalizable. So that is fundamentally what we're going to use. We're going to think of A transpose A instead of A. So the singular values of a matrix A are the square roots of the eigenvalues of that product A transpose times A, and they're denoted by sigma. So our eigenvalues are traditionally denoted by lambda, our singular values are denoted by sigma. And if you think of A transpose A as a form of squaring A, then it makes sense that if we look at the eigenvalues of quote unquote A squared, then the singular values, the sort of corollary to that for A, would be the square root of those eigenvalues. And it is a fact that if A has R non-zero singular values, then the rank of A equals R. I'm giving you all of these facts and theorems, and there are reasons behind them, and we're not going to dig into that now, but if you're curious, you're welcome to sign up for virtual officers and chat with me about that. But for now, you're not responsible for knowing why, just believe me and take it on faith. Okay, so the fact that the number of non-zero singular values that A has as its rank is actually super useful. We use this in computing all the time. So if you use our traditional way of calculating the rank of A, which is the number of pivot positions in our columns, then it's really easy to get that off a little bit because of rounding errors that a computer might make. So we might have something that should be 0, but instead looks like, I don't know, 0.00005, and that would be a pivot position, when in reality it's just a rounding error. So it's much easier. What people tend to do is they tend to calculate the singular values instead and round those singular values and say, okay, how many non-zero singular values do we have? That's going to be our rank. Okay. So this leads us to our central theorem, the singular value decomposition theorem. We usually call this SVD instead of singular value decomposition. And what it's telling us is we're going to let A be an arbitrary m by n matrix with rank R. So we have R non-zero singular values. And that means, so then there exists an m by n matrix sigma that is sort of our pseudo-diagonal matrix. And sigma is going to be composed of some blocks here. So the upper corner is actually a diagonal matrix, and the rest of it is zeros. So our actual diagonal matrix is going to be this matrix D, and the diagonal entries are the first R singular values, so all the non-zero singular values. And we're going to arrange them in decreasing order. There also exists two other orthogonal matrices, one m by n and one n by n, so that we can decompose A into U sigma V transpose. So this is our quote-unquote diagonalization that we've been trying to accomplish, so that we're factoring A into a pseudo-diagonal matrix sigma, and U and V transpose are like our P and P inverse. And we can do this with any matrix A. Notice that we had no assumptions about A at the beginning. So this is a really, really powerful factorization. So how do we find the singular value decomposition? Well, we're going to start by calculating that symmetric matrix A transpose times A and find all of the eigenvalues associated with it. And then we're going to find a corresponding set of orthonormal eigenvectors. So this is exactly what we were doing in section 5.3. We find those eigenvectors by simply finding the bases for the eigenspaces correlated to those eigenvalues. Okay, so once we have our eigenvalues and our eigenvectors, we can build our sigma by putting the singular values along the diagonal. So we just take the square root of the eigenvalues from part 1. And then we build our V by putting the orthonormal eigenvectors we found in part 2 as our columns. So we just need to make sure that we're keeping the relative order like we were doing when we were building P and D in section 5.3. Finally, we're going to build our U, and the ith column of U is going to be 1 over the singular value times A times the corresponding eigenvector. That sounds complicated, but it's just a matrix multiplication. And then we fill out the remaining columns by extending our existing columns to an orthonormal basis for Rm. Don't worry too much about this step. We don't actually have the tools to be able to do this, and I won't ask you to. So if I do ask you to find a singular value decomposition, it will just be find the eigenvalues, find the eigenvectors, and then the U's will just be 1 over sigma I AVI. So let's look at an example of how to do this. So we want to find the singular value decomposition for this matrix A. And notice that it's not square, it's a 3 by 2. So our standard techniques for doing this aren't going to work. But we can use singular value decomposition. So what's our very first step? Our very first step is to find the eigenvalues associated with A transpose A. So actually before that, we have to calculate what is A transpose times A. So A transpose times A, we'll take the transpose, and our first column of A becomes our first row of A transpose, and our second column of A becomes our second row of A transpose. And we go ahead and multiply that with our standard A matrix, 1, 5, 0. And when we take that product, you'll get a 2 by 2, and I got 74, 32, 32, 26. So here's our A transpose A, and now we want to find the eigenvalues. And we find the eigenvalues exactly the same way as we've been doing this, which is namely taking our A minus lambda I. So in this case, that would be 74 minus lambda, 32, 32, 26 minus lambda. And then we take the determinant of that to get our characteristic polynomial. So that's 74 minus lambda times 26 minus lambda, so our on-diagonal entries, subtracting off the product of our off-diagonal entries. And if you simplify this down, you'll get lambda squared minus 100 lambda plus 900. And we can further factor this polynomial into lambda minus 90 times lambda minus 10. So that means that our eigenvalues are lambda equals 90 and lambda equals 10. So we found our eigenvalues. Our next step is to find our eigenvectors. So these would be the bases for our eigenspaces. So since we want to put this in decreasing order ultimately, let's start off with the bigger one, lambda equals 90. And we find our eigenspace by actually plugging 90 in for lambda in our A minus lambda I matrix. So in that case, this would be minus 16, 32, 32, negative 64. I think that's right. And we go ahead and look at the corresponding homogeneous system and row reduce down. So this would be 1, negative 2, 0, 0, 0, 0. And this should give us the solution set to this would be our eigenspace. So in particular, we have a solution set that looks like x2 is our free variable, and there's 1 copies of x2 and x2 and 2 copies of x2 and x1. So this will be our vector that we're going to be focusing on, our basis vector. Okay, but that's not actually sufficient for v, right? V, we wanted this to be a unit vector because we want v ultimately to be orthonormal eigenvectors. So let's go ahead and find the corresponding unit vector to this. So we find the unit vector by looking at 1 over the length of our vector and multiplying it by the vector. So here, 1 over our length is going to be 1 over the square root of each of those components squared. So 2 squared is 4, 1 squared is 1. So it's 1 over square root of 5 times our 2, 1. So our first vector here is going to be 2 over the square root of 5, 1 over the square root of 5. Okay, and that will be our first column in our V. All right, let's take a look at our next eigenspace. So this is associated to the eigenvector 10. And if we subtract off 10 for our lambda, we'll get 64, 32, 32, and then 26 minus 10 is 16. And we can simplify that down to 1, 1/2, 0, 0, 0, 0. Okay, so our x here, if we think of x2 as our free variable, then we've got minus 1/2 copies of x2 and x1 and 1 copy here. I don't love that fraction. So instead for my basis vector, what I'm going to do is I'm going to let x2 equal 2. So I'm just going to scale this up. So this will be minus 1 and 2. But again, this is a problem, right? Because we want this to be unit sized. So for our v2, we want this to be a unit vector. So we'll divide again by the length and multiply by b2 itself. Okay. And similar to last time, the length is going to be square root of 5. So this will be minus 1 over the square root of 5, 2 over the square root of 5. Okay. And because A transpose A is symmetric, these are automatically orthogonal because they belong to different eigenspaces. So these are automatically orthogonal, and we scaled them to make them orthonormal. So we now have our sigma we can make by putting our singular values along the diagonal and zeros everywhere else. So our biggest singular value is the square root of our biggest eigenvalue, which is 90. And then our next singular value is the square root of the next biggest one, which is 10. And we fill in with zeros everywhere else. We know this should be 3 by 2 because A was 3 by 2. And then our matrix V should be those vectors that we already found. So our first column should be the one corresponding to 90 because that's what we put in our first spot of sigma. So it was 2 over square root of 5, 1 over square root of 5. And then our second column is going to be our second eigenvector that we found, which was minus 1 over square root of 5, 2 over square root of 5. So we found our V and we found our sigma. We're so close to being done. We just need to find our U. So our first column of U should equal 1 over sigma 1a times v1. And we know what all of those pieces are, right? So sigma 1 was the square root, was the square root of 90. And then a was what we were given right at the beginning, 750,150. And then v1 is our first eigenvector that we found. So the first column in v, so that's 2 over square root of 5, 1 over square root of 5. And I'm going to go ahead and factor out that square root of 5 and put it over with the square root of 90. So that becomes 1 over square root of 450. So we can maybe factor out a 15 squared. So that's 1 over 15 square root of 2. Okay, so now if we actually multiply these out, we've got 7 times 2 plus 1 times 1 gives us 15. And then 5 times 2 is 10, plus 5 times 1 is 15 again. And then 0 times 2 is 0, plus 1 is 0. Okay. So our first vector u1 is going to be 1 over the square root of 2. Didn't make that big enough. 1 over the square root of 2, 1 over the square root of 2, 0. All right, so I just multiplied that 1 over 15 square root of 2 in. So that was u1. I'm going to have to go to the next page, so hopefully we remember what each of our things is here. Let's copy this over to our next page. So this will give us our sigma and v. That's all we need. Copy. All right. So, all right, so here's a really messy version of our sigma and v. I'll clean that up for the actual notes. Sorry about that. And we found our u1, now we want to find our u2. So our u2 should be 1 over sigma 2 a v2. And sigma 2 is square root of 10. And then a, again, was 7. Our first column was 750. Our second column was 150. And then we multiply that by our second eigenvalue that we found, or our second column in v. So it's minus 1 over square root of 5, 2 over the square root of 5. Okay, and that equals, well, I'm going to again pull out our 1 over square root of 5. So that would give us 1 over square root of 5 times square root of 10 would be square root of 50 would be 5 square root of 2. And then we multiply that by 7 times negative 1 is negative 7 plus 2 is negative 5. 5 times negative 1 is 5 plus negative 5 plus 10 is positive 5, 0. So our u2 should be, if we distribute this through, negative 1 over the square root of 2, 1 over the square root of 2, 0. Okay, so we now have all of our pieces. So now we just need to make A. So A should be U sigma V transpose. So our U should be 3 by 3. So our first U1 that we found was 1 over square root of 2. Ooh, sorry about that. 1 over square root of 2, 1 over square root of 2, 0. Our U2 that we found was minus 1 over square root of 2, 1 over square root of 2, 0. What do we do for our third column? Well, we'll notice that the z coordinate doesn't have anything in it. So if we want to extend this to an orthonormal basis, we'll need the z column. And I'll just make the z column be 1 so that that's a unit vector. If that didn't occur to you, don't worry. Again, I'm not going to ask you to do that. So there's our u. And then our sigma was our singular values on the diagonal. Square root of 10, 0. And then our v, actually, we're not going to copy this directly because we want v transpose. So our first column of v will be our first row of v transpose. So 1 over square root of 5, or 2 over square root of 5, 1 over square root of 5. And then our second column will be our second row of v transpose, minus 1 over square root of 5, 2 over square root of 5. And that is our factorization. So to recap, if we want to factorize into singular value decomposition, what we do is we find the eigenvalues of A transpose A, which is a symmetric matrix, so it's going to be square. And we find the corresponding orthonormal eigenvector set, which we know exists because A transpose A is symmetric. And then we use that eigenvector set to give us our V. We use the singular values, so the square roots of those eigenvalues, to give us sigma. And then we calculate out the columns of U. And that gives us a factorization that works for any matrix, no matter the size and no matter if it's ordinarily diagonalizable or not.